Hello, everyone. Welcome to the Danish Robotics Research Seminar Series. This is the first of 4. I don't seem to have a screen, even if I have an audio stream. Welcome to this Robotics Research Seminar Series, where we're trying to give you an introduction into this. I'm Henrik Christensen. I'm a professor at UC San Diego. I'm a Dane by birth. Got my education in Denmark, still have strong ties to Denmark. And I will sort of host you through this series of 4 different seminars. I'm sure you know a lot about what's going on in Denmark in robotics, but you will typically have the association of universal robots, mobile industrial robots, blue ocean robotics, etc., etc. So there's a lot of awareness about what is going on industrially, but maybe there's a little bit less awareness of all of the really nice stuff going on in the academic community. So we want to use this seminar series to take you through sort of the research landscape in Denmark. We will have 4 seminars, 4 times 90 minutes. We will start in Odense, then we'll go to Aalborg, then we'll go to Copenhagen, and the last seminar in December, we will have a panel discussion where we discuss sort of the industry academia collaboration and knowledge transfer that you see in Denmark, which has been incredibly successful. So this is an interesting opportunity to go in and actually learn about all of this. And you would be surprised, Denmark has a very diverse research landscape with a lot of really cool stuff. We'll be starting out in Odense, in many respects, sort of the capital of robotics in Denmark. It's an interesting place. It was the birthplace of Hans Christian Andersen, so they are very good at fairy tales as well. A lot of the success you see in Odense actually dates back about 30, 35 years. Maersk, the largest shipper in the world, started out by building the most modern shipyard in the world in Odense. And it was incredibly successful. Eventually, salary pressure from Southeastern Asia implied that it was actually very hard to continue this. Nonetheless, because they were using a lot of robotics technology, mainly actually from applied math of all places, this led to sort of the embryo of building a research community in Denmark around robotics in a wider scale. And it led to the formation of an institute in Odense, the Maersk Institute for Production Technology, MIP, that has sort of been the starting point. And this was where UR started. This was where the people that sort of came to mobile industrial robotics, this was where Blue Ocean had all of their starting point. So it's been a very interesting birthplace for all of the robotics you see today, and there's a very strong ecosystem. So it's really nice to see all of this. To give you sort of the longer version of the story, I'm going to hand over the microphone to Henrik Petersen, who is the director and the section lead at Odense, and he's going to take you through the landscape. So Henrik, it's all yours. And we all named that Henrik in Denmark. That's just how it happens.
Yes. Good evening, everyone. Or good afternoon. Good morning. It's frankly speaking, I'm also not so used to these webinar series, so we'll try out slowly here, and I'll try to shift to the next slide and start telling you about what robotics we have in general and a bit about what is going to happen today. So we just here just the agenda for today. We just heard the introduction, very nice introduction by Henrik Christensen. I'll now give you a short welcome to robotics here at SDU, and then we have a lab tour, which has been some of it prepared, some of it will be done online here with 4 different sessions, and then there will be a farewell at the end. So if you look at what kind of robotics we have at University of Southern Denmark, we can look into different areas we have, and that's the original area which was with the shipyard that Henrik just mentioned, namely robotics for industrial manufacturing. This is still probably the biggest area we have, but other areas are also growing, in particular, for example, drone technology, where we have a lot of activity also now. I'll briefly discuss that at the end. Then we have activities in medical robotics, which Rajit will talk about later today. And we also have some cool robots that maybe not are extremely application oriented yet, that Poramate will also talk about later on. We have robotics for elderly care. We have around 100 robotics researchers across the different sections. And when I say robotics researchers here, these are really robotics researchers. It's not like we're counting every engineer. These are 100 people working within the field of robotics, more or less purely. If you look at education, we have a robot systems engineering education. We actually have two. We have a Master of Science and a Bachelor of Engineering education. In the Master of Science education, we take in around 125 students per year, and in the Bachelor of Engineering, 75 students. So 200 new students go in here per year. Also in relation to medical robotics and welfare robotics, we have health informatics and technology, which has an intake of around 30 students, many of them also doing robotics. We luckily also have a lot of local companies that Henrik also briefly mentioned, two of them, which I will also put on circles here around, namely Mobile Industrial Robots and Universal Robots, that are probably known to most of you, but many of the others are kind of still small robotics companies. There are also international companies mentioned here, but a lot of the companies you see here are local spin-off companies like MIA and Universal Robots that both came out of the university. So that's where our students go. So we have a lot of students that come in, but also a lot of places where they can get jobs afterwards. So I am also the lucky person that will take you through the first of the four small episodes that we will have now. So this was a general introduction to the university and what robotics we have here. So now I'll start with automated layup of composites, which is the first project, so-called flex draper project, that I will go through. So what is the task here? So you can see in the picture to the top right that it's about placing fiber plies. These are these mats. You can see they are very thin mats, fiber mats, that needs to go smoothly onto a double curved structure. This is done today manually, and it's a very tedious and cumbersome process to do that. And it has a wide range of applications within aerospace, automotive, and wind turbines, other areas as well. Wherever you have high quality composite components, this process is relevant. And it has therefore also been tried for many years to automate it, but there are quite some difficulties with this that I will also discuss with you when I'm now introduced the project, namely Flex Draper project that we have been working with, mainly funded by Innovation Fund Denmark. There are 3 universities participating, and these are by coincidence the 3 universities that will also participate in the webinar series here, namely SDU, Aalborg University, and DTU. Then there are 3 companies, namely Therma, which produces the composite parts for aerospace. These are Therma is the first end user, the proactive end user we have for this. Technikon is the one that is going to commercialize the system that we develop. NLR is the Dutch version of DLR, which is maybe more known. It's the Netherlands Aerospace Center, and there we have persons acting as a consultant, helping us with all the issues that are in automating these kind of processes within aerospace. Now, before I go into more detail with technology, I will show a video that will illustrate the different components and also how it runs. So what you see at the top right with the big robot is kind of the system we have. and I will show a video and I will be silent for a while the video is running. My name is Henrik G. Petersen. I'm a professor and head of section of SDU Robotics, and what I'm going to tell you about now is the flex draper system. It's a rather complex system, so we start with a 6-axis KUKA KR 360 robot. And the end effect of the robot is mounted a drape tool, and this is a specialized tool for handling the picking and draping of the plies. So we have in total here 60 suction cups. Each suction cup are mounted on a linear actuator so that we can move up and down. But in addition, there's a universal joint that allows the whole actuator to pendle. And then there's a spherical joint at the top, at the bottom, allowing the suction cup to reorient. And the idea is to have a simple system with only 1 degree of freedom per suction cup. The rest is handled by passive compliance to the mold on which the plies are to be draped. Between the suction cups you can see there are springs, and these springs is in order to give a natural interpolation, so that if you have that the actuators are at different heights, then the suction cups will automatically orient themselves in a natural way so that you interpolate a curved surface. In that way, you can, by only 1 degree of freedom per suction cup, for most double curved surfaces, you can actually shape the array of suction cups very neatly to the surface. Here you have the pick table. So here the plies are located. They are actually placed randomly on the table here. So the first step is by the camera up there to detect exactly the position and orientation of the ply down here on the flat table. As you can maybe see, there is a foil on the ply, and this foil needs to be removed. So the first step is that this robot then goes to the corner and removes the top foil here. Then the big robot that we discussed before goes and pick up the ply, lift it, and then the bottom foil is removed with a robot. So when we move between the pick table and the mold where we drape the plies, we check before that the bottom foil has been removed with this camera that you can see down there. We can at later stages also check that the whole shape that is created when moving the suction cups is also correct. So it's kind of a test in between here that the process is okay before we drape the ply. At the other end, we have the mold onto which the ply needs to be placed. So here you can see a placement here, and it's very important that we get the exact position and orientation of the boundary of the ply. But what is even more important is that the ply gets smoothly onto the double curved surface. So it's not allowed to have any wrinkles or air pockets in when the process of laying it down here is over. Therefore, we need not only to be able to model the tool, but also to understand that when we place the ply, how does the ply itself, being a deformable material, behave. The ply is a fiber ply, so we have fibers in perpendicular directions where it's basically unstretchable, whereas it's quite stretchable in the diagonal directions. And we need to stretch it in order to get it smoothly onto the double curved surface. After we have placed the ply or several plies, there is an automatic debulk. This can go down and create vacuum here, so we can do a last suction so that we get it completely stuck onto the ply underneath. Both before and after debulk, we check that the quality of the drape is as good as it needs to be. So up there you have a camera that simply checks that the ply has gone smoothly onto the ply underneath. This is done, as I said, both before debulk and also when you have done the debulk and you have sucked it completely on, you again test that there are no undesired wrinkles or air bubbles left. The overall process is programmed on the computer using a German programming environment called VEOSIM. So it consists of building blocks that are sub-processes that are concatenated together to the complete program. So the idea is then that once we have done this, we are ready. And now we just need to press start and then the complete sequence runs. Yes, so now after this little video, I will describe in a little more detail some of the key components of the system. Not all components, but the most important ones. The first one I will not dwell long over because it is this VeoSim programming environment where we have these service blocks that we concatenate to the complete program. Christian will talk a lot about the technical part of this VeoSim later on today. But I would like to stress that each of the blocks are based on models, and these models are crucial to get the system to work because every ply is different in shape, every layup is different. So everything has to run model-based and automatic. So I will now discuss some of the models for this. There's first the models that we use for the behavior of the ply. So when we on the computer is testing the system, that is, we are doing trials, virtual trials on the computer, we used fast computable model. They are basically interpolation models between the suction cups when we search for solutions. With these interpolations, we can then predict where we hit the mold and so that we get the correct laydown on the mold. When we have then done that, when we have found out on the computer what is what seems to be the correct solution, then we can execute a more time-expensive final element-based model for a more reliable verification of that everything is as we expect. So these are the fiber models for the system. Then there's also the tool. I believe I was maybe a bit unclear about degrees of freedom and actuated degrees of freedom. There is one actuated degrees of freedom per suction cup, and then there are 5 passive degrees of freedom, namely 2 at the universal joint at the top. You can see on the picture to the left here, and then there's a spherical joint at the bottom. It can hardly rotate around the vertical axis though. So we're close to only having 5 degrees of freedom passive, 4 degrees of freedom passive. You can see a bit of the spherical joint to the right. So then when we need to predict the configuration, when we do the simulation, we need to predict the configuration of all the passive joints, that is the position and orientation of all the suction cups. So we simply have a model for the potential energy, including spring, gravity, and other artifacts. And we simply assume that the motion is slow enough, so it's enough to minimize the potential energy under the constraints that, of course, the actuator positions are at their known values and that there are no mold penetration. With the modeling, we are doing all the simulation as it also was illustrated in the video, but still it's very, very important that there are no mistakes. So after laying down, we have a quality inspection, quality control, which we do use a structured light approach for. These are very black materials, but we have a knowledge about the shape of the previous ply that was placed, and we basically know that it needs to be the previous ply plus around 0.3 millimeters of thickness of the ply. And then if there are air pockets, wrinkles, and so on, you see pictures as the heat map to the right, where you can see that there are places where it doesn't look quite as it should. It should be noticed that before debulk, some small air pockets, like the one, if you look at the three sketches at the bottom, the soft air bubble to the left will actually disappear during debulk, whereas a sharp one in the middle will not. And we have a model-based system that we also test in reality for predicting which kind of air intrusions can be accepted and which cannot. We take a conservative approach to this, so we call an operator if we will call an operator if we believe there's an error. That was basically what I have to say about the FlexDraper project. So thank you for your attention, and there might be some time for some questions, but
So I'm going to be the next presentation now. We just discovered that comments in the YouTube channel are not possible because we allowed it to be for kids. So this will be something that we would have to work on for the next episode. Definitely, we will try to fix it along the way, but so far we can just continue with the next presentation. I'm going to talk about agile interaction with industrial robots, and I'm going to take you to our so-called Lego lab. And this is the problem that we want to address in this Lego lab. So we have collaborative robots. They are great for worker interaction, but they are of course limited to lower payloads. On the other hand, we have the well-established industrial robots. They are really scalable regarding the payloads, but they are limited regarding the worker interaction. We always have to make extra, pull up extra measures for safety if we want to have workers closely cooperating or collaborating with the industrial robots. And this is what we address in our group with several technologies: service-oriented architectures, database technologies, digital twins, visual programming, and we are going to have a look at them as we use them in the Lego lab and in the I4O lab at SDU Robotics. Let's start with this first scene here. So this is the assembly sequence of injection molds from Lego. Those injection molds at Lego need to be assembled and disassembled on a regular basis in order to wash the assembly, the injection molds, and in order to exchange the interior parts of the injection molds on a regular basis. This is today carried out manually. And you can already guess from this injection mold here that this is a very tedious task. Also, the injection mold is quite heavy. It has 120 kilos, the one that we look at here. And this is the smallest that Lego had to offer for our project. So they can be way bigger and weigh up to 750 kilos and be even more complex than what we are looking at here. So together with Lego and with KUKA, we want to offer the workers a new workplace where they can make use of the two robots that we see in this scene here as well, in order to get help when assembling and disassembling the injection molds. We have the large KUKA on the right-hand side, a KR120, that is supposed to carry the injection mold assembly and to move the assembly to preferred positions and orientations. Then we have on the right, on the left-hand side, the Kukaiva robot equipped with an industrial screwdriver that is then approaching the assembly in order to screw the bolts and torques to given the screws and bolts to given torques. And the worker comes in from our perspective here. So the worker is supposed to put together the injection mold in coarse steps and then to trigger the actions of the two robots in this scene. What do we do in order to get to this assembly sequence as we have seen it? We went to our I4O lab, and here we have a quick run through the lab, and there we have a VR setup that we used in order to take in the CAD data that was provided by Lego of the injection mold. And this is now what we see in the VR here. And based on the VR system and the CAD data, we are taking apart the CAD data in the VR in order to actually generate a disassembly sequence to start with. And this disassembly sequence gives us an order of steps, as well as directions of in which direction to take out the parts. And if we, so to speak, turn this disassembly sequence around, then we have a good first approach regarding an assembly sequence that we can then use in order to generate some first programs for this interaction of the worker and the two robots. So we take this digital format of the assembly sequence that we have generated in VR, and we bring it to this service-oriented architecture. We work with this service-oriented architecture in order to actually combine and link the digital twins, virtual replicas of our setups on the left-hand side, to the physical assets on the right-hand side. So the real machines we have in our lab. And from the many projects that we have carried out with our industrial partners, and also, for example, the project that was just mentioned by Henrik, FlexDraper product, we always come across the same problem. We somehow have to combine methods that we have on a planning layer, so user interfaces, simulation and model-based control, with real-time layers and methods like controllers and low-level control that are tightly linked to the physical assets, to the real machines we have in our robotic setups. And we now do this combination or recombination based on the abstraction layer that we see in the middle here. This abstraction layer consists of services. So services are wrapping our simulation-based methods or planning methods, as well as our real-time methods, like, for example, motion execution for the robots, also control of the screwdriver, also control of sensors. This is all wrapped into services that we can call from within this abstraction layer, and that we can also use on the high-level planning layer side to already work with the services without directly assigning the physical assets to the actual service. This comes then later in the project. This comes then later in the process of a planning until we really want to go to a specific physical work cell. Now, the core piece, and that was already mentioned by Henrik, is this service block. This we use for visual programming, but also to encapsulate expert knowledge into a service that is then usable by workers as well as other experts. So we have some input parameters, like, for example, execution parameters, for example, for a motion service. With the robot, this would be the target pose in which we want to move. And this comes from a database. And the output parameters are then results or the status of the execution status of the service block. And the clue is that we have some service logic that allows us to use the very same service block here with a simulation engine. This could be our own system, or this could also be a different simulation engine, like, for example, MATLAB or other nodes and ROS, as well as execution engine. So we can switch from simulation to physical execution, and then the very same service will be carried out just with a different backend, so to speak. The execution engine would then make use of ROS or MQTT or OPC-UA in order to address controllers that are close to the hardware, close to the physical assets. And this is what it looks like then in the digital twin. So in the upper part of the window here, we see the large robot, how it is presenting the assembly to the worker. Then the worker does some steps. And then we have the collaborative robot kicking into action in order to screw the given bolts here to a given torque and to tick off the quality of the assembly in a digital assembly sheet, so to speak. And at the bottom of the screen, we see how those service blocks come together to a network and how they're executed one by one by one. This is now a very sequential network that we are looking at here, but it can also be a concurrent network. It could be a tree hierarchy, really, where we go into any type of graph oriented structure for our programs. In the upper left corner, in the upper right corner, we see the operator view. So this is something that we are going to see in a second also in the real workplace. So still the operator is in charge of the operation and has to acknowledge all the different steps, step by step by step. This is with the current state of the workplace, what is necessary in order to guarantee worker safety and awareness of the steps and the process. And this is then what it looks like in our lab. So here we have the KR120. Here's the injection mold. And here's our colleague who is taking the role of the operator or the worker and puts together the assembly steps. He is acknowledging the steps on this tablet that is part of his workplace. And then the collaborative robot comes into place. The EVA is taking care of making sure that the screws are in place and that we come to the execution. This is now a service framework that, in the case that we currently have looked at, brings together the application from Lego with the robots from KUKA. We are using the service framework in order to make KUKA robots available for Lego in this case. But as you could already have seen it from Henrik's presentation just a minute ago, we have many other partners. So, for example, our partner Danfoss, they like to make use of the same service framework, but they prefer to work with KUKA robots and UR robots in mixed setups. Or we can even extend this service framework to totally different industrial sectors. So beyond factory automation, beyond manufacturing, we, for example, work together with Cobot, which is a Danish company that is building 3D concrete printing systems for the construction industry. And we are currently working together with them in order to deploy the same service framework that we are looking at here for their actions and their mission to bring more robots to the construction sites. Just to give you an impression how this is expandable to different applications. So this is now back in our I4O lab at SDU. And here we have an assembly setup with two universal robots working together on the assembly of drone parts. So this is a small assembly line that we have in our I4O lab in order to try out the latest technologies in Industry 4.0. And we are assembling drones in this setup for our people in the drone center. And this setup makes exactly use of the same service framework. And this is our team, which is working together in the Lego lab as well as in the I4O lab in order to bring this service-oriented architecture into place. And if you now watch this presentation and if you think this is actually quite a nice topic and interesting partners to work with and a nice team as well, then please consider to have a look at this open position that we have currently announced on SDU job portal. It's a PhD position sponsored by Lego, and this is exactly about working with this Lego demonstrator and bringing new results, for example, taking into account workspace monitoring in the next version of this demonstrations. So thank you for your attention. And the next speaker is my colleague Rajit, and he is going to talk about medical robotics. Thank you very much.
Okay, thank you, Christian. Hello, everyone. So I will give a small presentation of the medical robotics research we do here at SDU, and take you through some of the applications that we have here. So first of all, a small introduction to the research strategy that we have implemented in the lab. We very much like to actually start with some problems, some concrete projects that originate from the healthcare sector. And this is very important for us because, as you have seen so far, in the industrial application, in the industrial domain, we have a lot of tasks to start with, and also to apply our technology and the ground research we do here. Whereas in the medical robotics area, it's difficult to actually find the right projects and the right problems to start with. And here we have a strategy to actually go to the hospital, talk to the doctors about exactly what to work with. And based on that, we can then investigate and implement our solutions and then bring it back to the hospital. That's a big point in our group, is that we really try to bring the technology back to the hospital, although this is very expensive in terms of research time, and often not rewarded in the community. Some of the projects that we do here, I've listed here. So we have a lot of projects based on AI-based data processing. And we have, of course, a lot of projects which are robotic applications. As you can see, they all originate from concrete problems within the medical field, and we try to apply the groundbreaking research that we do here in the medical domain. Today, I'll go through two small examples. One is a very long-term research strategy or project that we have, which is about surgical robots. And the other one is a very fast development project we did during the lockdown we had in Denmark on COVID-19. I'll come back to that. Two slides about the research on surgical robots we do. I believe that in the future we will have automated surgery, automated operations going on in our ORs in the hospital, where you don't have doctors remote controlling the task, the surgical task as they're doing now, but we will have robots carrying out pre-planned operations, and we will not have a staff in the OR all the time, but we will have a control tower like we know from the aeros. From the flight industry, where we supervise and we monitor the traffic, and here we will monitor the execution of the planned surgery, but and only interfere if there are a reason for that. Otherwise, we expect that the tasks will carry out as planned. And in order to build that up, we are working on a strategy here where we have 4 levels of planning and execution. And as we saw in the industrial application, it's about finding out what hardware do we have. Can we simulate the task in a simulation environment? Can we, based on the simulation, find the right recipe, find the right sequence of events that should happen in the program, and then based on that, we can then execute on the real robots. And one of the things that we do in order to test this out is that we have here a system where we are remote controlling the robots. But this particular setup has two different generations of tools. We have the DaVinci SI and XI tool combined in one application, and where we teach the robot how to perform a task, and then we can record it and play it back. So by doing that, we can combine different versions of the hardware to solve a particular problem. The reason we do this is that we believe that the robots that we implement in the hospitals should be combined in different types, in different combination, in order to solve a particular task. And this combination should not be dictated by the medical device manufacturer, but it should be guided or selected by the users. And by enabling this flexible programming and a flexible way of setting up the systems, we can then show that this is actually possible. The second example I have today is the COVID-19 development we did. And in this case, Denmark was locked down in the beginning of March. And once that happened, all the researchers at the university was sent home. And during that period, I had a lot of phone conversations with my colleagues at the hospital, whom I had all these projects with. And they were all diverted into preparing the hospital to receive a lot of expected patients at that time. And at that moment, during the conversations, I of course asked them, is there anything we can do to help you in this situation? And the thought that we had is that if we cannot help the healthcare sector at this point, when should we then do it? So I wrote down together with the doctors a plan to actually create an automatic throat swapping robot. If we could create such a robot, we would then be able to kind of protect the healthcare personnel with the first contact with the patients. We got in the first place, most of these we applied the plan to different fundings and sent it in, and we got rejected from a lot of funding sources because I don't think anyone believed in it. I don't think anyone thought that this would be possible, because we set the goal to be a 4-week project, and we would demonstrate that all of the disciplines, all of the tasks that needed to be done within automatic swapping, we could do that in 4 weeks. And we got no funding until one of the founders of Universal Robots called me up, and within a week he found the funding to actually start developing this project. I was given 10 persons within this project, and the first week we planned the project and started developing, and in week 2 we could do the first trials on a model of the throat, and basically see how the motion should do and how the force torque control of the robot should be. And within 3 weeks, we had the first human test of the system, and the project leader has to, take one for the team. So here we actually did the first swap of a human throat with a robot, we believe, and during this project, we took down from the shelf known technology where we have very specialized force control algorithms for this universal robot. And we put together this system to actually do the swaps. And at the end of week 5, based on the research we did here, a company was formed, Lifeline Robotics. And the current version of the robot we developed here looks like this. And here is a video where you can see the entire process as it is right now. So what we see here is that the patient is first given some instruction to how the system will work. They will scan their ID card and they will sanitize their hands. The robot in the meantime will prepare a sample. They will walk up to the robot and a vision system will identify where to swap the patient, go in and do the swap, and afterwards seal the sample, put on the lid, and transport the sample into a container, which will then be taken further to the analysis process. And currently this robot is being made ready to go through the CE approval process, and hopefully very soon we will see it on in the hospitals helping our healthcare workers. So to wrap up this talk, what I do and what we do in my group is to take basic research that my colleagues do and then apply it to the medical domain. And within that domain, we have a very clear stated research strategy where we want to apply the solutions back into the system in order to actually gain some momentum. Thank you for your attention, and I'll pass the words to my colleague Ko, who will talk about bio-inspired robotics.
Okay, hi everyone. So just give me a few seconds. So I'm trying to share my screen. Just a moment. Okay, so hi everyone. My name is Poramate Manoonpong. I'm from the SDU Biorobotics. So you have heard from my colleague on the different robotics like industrial robotics and medical robotics. So today I would like to give you another perspective of robotics, which is inspired by natures. Here, let me start first with our video. Please enjoy. Okay, so that was a bit of short introduction to our research. What you have seen there is basically we have developed a bio-inspired robot, which is inspired by nature. That's what we are basically doing research in our unit or biorobotics sections. Here we do two things. The first thing is that we try to look into nature and we take the nature as our inspiration to develop new robotic technologies. On the other hand, we try to use our robotics technologies as a platform to test a new hypothesis, to find a new research and understanding and keep fighting in natures. We have 4 main research topics in our sections, which include like bio-inspired legged robot, swarm robots, soft robots, and also neuromorphic robots. And today I will mainly talk about the bio-inspired legged robots. From the video that you have seen, now I want to walk you through the process, how we can develop the robot control technologies to achieve complex locomotion like natures. Here, this is our robotic platform that we have recently developed, which is based on an insects. The robot called Morph or Modular Robot Frameworks. The robot is mainly developed by our PhD students, Matthias Thor. The idea of this robot is that basically we look how the functionality or the biomechanics of the insects look like, and then we try to abstract those features into our robotic system. Morph is a robot platform that you can reconfigure the leg system of the Morph from 6 legs into, for example, 4 legs. And we have different type of sensors. In total, this robot platform has something like more than 150 sensors, that including like current sensors, joint angle sensor, 3-dimensional force sensor, and so on and so forth. And this robotics platform is also can be used as a research as well as for education platform, and it has also a ROS interface. So this is our robotic system that we are using as our platform for study natures, how locomotion works in natures. On top of this, we look at the locomotion control mechanisms. For example, if you look at this kind of little cockroach, we can see that in terms of the locomotion system of cockroach, it consists of a kind of neural networks. It consists of many neurons. And from this point of view, we try to develop our neural control of the hexapod robots that try to mimic the locomotion behavior of the cockroach. And this is kind of the neural networks that we have developed. And from this neural network, so let's just go a little bit deeper inside. So this network consists of just kind of a 2 neuron system. As you can see here, like we call this is kind of central pattern generators. This network can generate basically like basic rhythmic patterns. And by using the machine learning algorithms that we have recently developed in our group, we can adapt the neural parameters online in the very fast time scale. This means that we can find the proper frequencies that match to the platform. For example, you can generate the you can initialize the frequency in different frequencies, for example, and after a few period of time, the system can learn to find the proper frequency that match to this robotics system. For example, here in this video, we start from the very high frequency, and after a few seconds, now the system learn to adapt to find the proper frequency, like from 0.2 now to become like 0.27, which with this frequency, it makes the system work more efficiently. And also, we can use these learning algorithms to let the robot react and adapt its locomotion speeds or its frequencies to match to its internal state. For example, what we show here is that when you have a robot that fully drive by full power capacity like 15.5 volts, it can walk with certain frequencies, and later on you will see that now we start to decrease the power consumptions, or we try to decrease the power supply to the robot such that the robot cannot walk efficiently like before. Now the power is dropped down. By using our control technique, the system can quickly adapt to find a new walking frequency such that it can map to those states of the system. And if you return the power to the full mode again, the system can quickly readapt to the previous original walking speeds. And this is a kind of the fast online autonomous machine learning that we have developed in our research group. Besides this, we start to look at the another type of the neuron systems, saying that when you generate the complex locomotion like the cockroach, or like dung beetle robot that can walk or it can manipulate complex objects, in that case you need to find the complex motor patterns that you cannot just drive the system with the rhythmic patterns like standard rhythmic pattern like this as before. But you need another intermediate network that can adapt the original rhythmic pattern into a more complex patterns like this, such that the leg or the system can move more efficiently and can deal with more complex behaviors. Here, this is our simulation results. We apply a machine learning technique to let the robot online adapt its locomotion behaviors. Like in this case, the robot can learn after a few, in this case, it takes like less than 5 minutes to let the system learn and find the right locomotion patterns to deal with the setup like this. And also, if the robot faces to some unexpected situation, like for example here the robot walk and suddenly we block the leg or we damage one of the leg, the system can readapt immediately to find a new walking patterns such that the system can now it's got blocked, or one of the leg that you can see here, it got damage, imitate like damage situations, and the other leg start to move in the different slightly patterns such that the system can still continue moving forwards and to complete its missions. And this is a kind of the machine learning for motor pattern adaptation that we have developed in our research. And on top of this, we apply the same technique into our dung beetle-like robots. This is the robot that we have recently developed based on the little insect, the dung beetle here. The interesting aspect of this animal or this insect is that it can not only walk, but it can also use its legs to transport a large ball. For example, this ball could be the weight up to 10 times of its body weight. And our vision is that we want to develop a robotic system that can perform or can transport a heavy object like the dung beetle. Just imagine in the future, if you can have a robot that can move an object like more than 10 times of its own weight, how efficiently of the system can you have, and it will bring up to a variety of applications like construction and transportation and so on. And that is our starting point of our research. And in this case, we use the same kind of the neural control to let the system learn to find the right locomotion pattern for this alpha robot or the dung beetle robot, which is developed by our PhD student Petersen. And this is the simulation showing that, let's say, after 150 iterations, the system can find the right locomotion pattern for this dung beetle-like robot. And now we are moving further, try to find the proper locomotion and manipulation patterns such that the robot can not only walk, but it can also transport and roll a large ball. So with this, I would like to wrap up our short tour today about our research at our research unit at Biorobotics research unit. So today we talk on the bio-inspired robotics morphologies and also bio-inspired neural locomotion control, with especially on the frequency and motor pattern adaptations. So in these frameworks, so we try to create also a new concept of develop the robot system like embodied neural robotics and want to move toward like soft human-machine interactions. So, and with this, I would like to thank all my research team, and this is our research group at SDU Biorobotics. And I think so, I would like to now pass my next to my colleague Henrik for the farewell presentations. So thank you for your attention.
Yeah.
Okay, so I think it's Henrik and Henrik back to sort of say, you know, you saw an amazing view of what is going on around Odense, from manufacturing to new ways of doing things, all the way to nature inspired to medical. So it gives you a pretty good sense of what is going on around this and the very diversified portfolio. But it was also very important what Henrik said at the beginning. They have 200 new students entering their program every year. So this is a people factory as well. It's not only generating sort of interesting new things. So it's very important to do this, and it's very inspiring. So Henrik, before we sort of wrap it up, what is your? Can you talk a little bit about where do you recruit students from? Mainly from Denmark, or from all over the world, or where are they from?
On the students that enter at to study a bachelor degree of science or engineering, it's mainly from Denmark. The master students are both bachelor students coming up from our university, also from other Danish universities, but approximately half of them are from the rest of the world. I would, before I wrap completely up here, say a few things about further things about SDU, but before I do that, I try to click here, but it doesn't work. Now it does. So we had a little hiccup along the way concerning the possibility to ask questions and comments. We try to mitigate that by making it possible for you to send questions and comments to Christian. Plus, when we upload the video to YouTube, there will be a possibility to make comments there as well. And please remember to subscribe to the channel for all the upcoming videos, etc. Then just to say that we have other robotics. So we didn't show all the robotics we have at SDU. We have, for example, robotics for elderly care, both trying to, so the person at the top is clearly not an elderly, but this illustrates helping elderly people with manual tasks. At the below, it's rehabilitation. So it's a universal robot acting as a physiotherapist, helping the elderly recovering their muscles. We have also a big area, as I mentioned at the beginning, within the drone technology. And in addition to being here at the university, we have, if you look at the map at the right, we have Hans Christian Andersen Airport, the airport at Odense. And we have this marked area where it's allowed to fly the drone, so we can do out-of-sight flights with drones at the airport. And there's a big facility for drones at the airport, in addition to what we have at the university. And that kind of ends what I want to say about SDU. And the next episode will be in Aalborg. And I will here leave it over to Henrik to now bridge, because he is kind of handling the overall series. So please, Henrik, could you say something here?
Sure. Thanks, Henrik. So we're trying to do this where we basically do one every month. So we had this one in Odense, which was a great starting point. We will return back to Odense in December for sort of a panel discussion. So in about 4 weeks, we will have this presentation in Aalborg, which is in the northern part of Denmark. They also have a long tradition of doing this, but in a slightly both sort of industrial robotics, which they have a very long track record of doing. They also have a lot of on rehabilitation, but also robots and the arts, for instance. So again, a very diversified portfolio. My co-host for the Aalborg will be Thomas Bach, who's a professor there and sort of the section lead of the robotics up there. So we very much look forward to seeing you back. And I promise we will find a way of enabling Q&A 4 weeks from now, so that we can make it interactive and you can directly sort of post questions as we go along. So I hope you've had a great time seeing some of the academic research. We're very much looking forward to seeing you again in 4 weeks, and we hope you have a great evening. Thank you.